I'm Dr. Bob Straight, and thank you to the program today. And in today's program, what we're going to talk a little bit about is how electricity flows through a wire. What is the mechanism, the underlying mechanisms that make electricity flow? Now, normally in a physics class or an electronics class, when we discuss electricity, what we're talking about is electrical effects, the effects of electricity on both matter and the electromagnetic field around it. Today, we're going to step down in our level of abstraction. In other words, we're going to get more detail. An analogy would be if you think of normal electronics classes as an car operator discussing how to start a car. Put the key in the ignition, turn it, step on the gas, and run while it starts. Okay? But today we're going to get down low. We're going to get into the mechanics level side of things. We're going to be discussing what happens when the key turns, how the key fits into the lock, what mechanisms take place in the lock, where's the electricity flow, how's the starter move, where's the gas coming from, how's the pump activate. We're going to be talking more at that level, the level of detail that you usually don't encounter when you're thinking of starting a car. Okay, so we're going to work around batteries, and the concept we're going to hear is how does a battery work? Why does it work? We're not going to just talk about the chemical electric effect that takes place when you have chemical reactions and you have electron transfer. That's the higher level. We want to discuss how is this taking place. So what we're going to do is discuss this in context of the ocean universe theory, which is a theory that describes how ether exists, and in this theory, we define ether and energy as one and the same thing. And what usually people, when they say something has energy or something is expending energy, that concept of energy is what we call force in the ocean universe theory. So force is potential force or kinetic force. Potential force is forces that can take place. Kinetic force is force that's in action. And normally we call that kinetic energy and potential energy. But we don't do that in the ocean universe theory because we have a deeper, more fundamental understanding of how these things take place. So what I want to talk about first is let's talk about what a battery is. And we're going to go to the board here and zoom into the board. Let me put this up on the board so we can see it. Okay, this is probably one of the very first modern batteries, and it's called a Leclanché cell. And the Leclanché cell is basically a glass jar. Inside the glass jar is a zinc electrode, and then there's some fluid, an electrolyte fluid. And there's like a clay pot inside there, and inside that's some carbon, and those are the two terminals. Now, this was first developed back in the 1800s, and it served for a long time as the standard form of energy sources for things like telegraphs and bells and different things. One of the drawbacks on this is that as you started to use it, it would downgrade very quickly, and but the positive side is if you stopped using it, it kind of bounced back and you can use it. So it was really common for intermediate use. So that led to a battery that we're more familiar with today, and this is a zinc, carbon zinc battery, and what this battery is we have a zinc pot around the outside, or right here. We have ammonia chloride, zinc chloride filler around the outside, and then we have a graphite or carbon cathode in the middle. All right. So, and then on the outside is a non-conducting shell usually today. And so the chemical reaction that takes place inside the ammonium chloride and zinc chloride paste causes a current flow, and we have power that comes out of both ends. It's a very simple design. You see them all the time. Today we're into a different type of battery with our lithium batteries and our nickel batteries, and those batteries are operate in the same fashion, just using different types of chemicals, but this principle is the same. So, going from lithium and nitride batteries, okay, we're going to put up here a very simple battery that anybody could make, and all it involves is two beakers and a U-shaped glass tube, and over here we have a copper electrode, and on this side we have a zinc electrode, and we have a voltmeter. Now they're using copper, but we're going to talk about this in context of carbon as we go along here, because it's more traditional than what you would see when you look at a battery. Now, the way this battery in theory operates, at least at the next higher level that we want to talk about today, is there's a chemical reaction that takes place here in the reduction of the element, the solution of the zinc sulfate and the copper sulfate solution, and we have electrons flowing up into the zinc. The electrons flow across the wire. See, the voltmeter measures it, that's our resistance. Then back into the copper electrode, okay, and the circuit is closed through this salt bridge. Now the interesting thing about this is that all of this material is conductive, okay? Just to give you an example, copper sulfate, for instance, okay, has a conductivity of 42.3, and zinc sulfate has a conductivity of 43.3. Okay, copper is 100. Okay, so what these numbers mean is copper is our standard, and then copper sulfate's conductivity is 42.3% as conductive as copper, and this is 43.3% as conductive as copper. Okay. Now, I want to also point out that, well, we'll get to that in a minute, but I just want to use, one of the things we want to also look at on these two is what are their densities? And we're going to find that density is directly proportional to conductivity, at least in what we're talking about today. And that's kind of a unique way of looking at this problem. Okay, so let's take this down for a minute. And let's look at something here, and we're going to talk about this in a minute, but let's just put it up here. Okay, here's a chart that just shows what the size differences would be for a conduit carrying the same amount of electricity. What size conduit would you need to carry it? So in here we see this, and you can see this, we'll blow this up on the video, but you can see where the copper size is here, okay? The silver is very thin, it's in here. I'm not sure why they're showing it so thick on this corner, but silver would just really be a thin line like that. Okay, gold conductivity is there. Aluminum's conductivity there, because silver is 101% is conductive, 105% is conductive. Aluminum is here. Brass, you would need this area. Iron, you would need this amount. And if you use bronze, which is a formed with brass and some other metals, you'd actually need this size surface area. So you can see that to carry the same amount of electricity, you're going to need different size conductors. And all of that will come into play as we move into the discussion here. Okay. So let's go about drawing our battery. And we'll make it a simple battery. And we have a zinc outer shell. Okay. And we're going to use blue here. And in the middle we have a carbon. It's a carbon. And we're going to seal this off with the green. And sealed off so that the materials inside won't leak out. And then inside here we have a paste, an electrolyte paste. So that fills up this whole area inside the battery. So when we look at this, this is the positive up here, and this is our cathode. It's the cathode right here. Down here is our negative, and that's the zinc. All right, now what we want to do on this is we want to draw a circuit, and we're going to draw that circuit, and we're going to come off this. Now we're going to come down here. Okay, so we've talked about electrical flow in the past, and what we call conventional flow would be the current flowing this way, and this is how it's normally depicted. Most people, when we're talking about batteries or electric power supplies, we think of positive going to negative. It kind of makes sense when you think of positive and negative. There's more going to less. But actually, what we call electron flow, the current is actually flowing this way. It's actually flowing from minus to positive, not from positive to negative. So when we describe it this way, we call it the conventional flow. Turns out that they described that back a long time ago, and afterwards they found out it was the other way, but everything had already, the conventions have been set. The batteries were labeled, all the equipment was labeled. Everything was already labeled with positive to minus. All the books were printed that way, so they can continue to do that type of approach. They call it conventional flow because it became the convention. But the actual flow is really the electron flow is going to negative. So we want to use the electron flow because we're talking about how do electrons move through pipe or through a wire. And the reason I use pipe is because we'll find out that it's just like objects moving through a pipe. Okay, so the basic principle of how we understand this, if you took an electronics class, is that the chemical reaction takes place in here, and a lot of times this is like a zinc sulfate or a copper sulfate solution in there, a combination of there. It could be also ammonia based electrolyte. But as a reaction takes place, frees up electrons, and somehow the electrons migrate down this wire and around it back to the cathode. Now, the first question that has to come to your mind is when you look at this, is we saw before that there's conductivity. So we have a carbon here which has a very high conductivity. We have a zinc around here that has very high conductivity, and then we have the electrolytes in here that we already talked about that had 40-some% conductivity. That means they're conductive. Conversely, air is 0% conductive. Okay, that means that electricity will not flow through air. Now, when we see an electric spark or something like that, electricity isn't really flowing through the air. It's flowing along ionized air molecules. So it's a little bit different. Air, in its natural sense, isn't an insulator. It's not until it gets ionized that electricity can move through it. So the question that comes up is, if we have some kind of electron activity going on in here, and we got little electrons forming like this, say, right? Why do they move through here and then come around through here and go around the wire to get to here, when they can just go to here? Why can't they just go from there to there? And we really don't touch that in classical physics. However, the ocean universe theory shows how this very same phenomena that creates what we call gravity causes this flow of electrons to take place going through the wire rather than directly from the electrolyte into the carbon anode. Remember, there's no insulation. None of these things are insulated. None of these components are insulated. The electrolyte touches the carbon, and the electrolyte touches the zinc. Now, the only thing that is removed from each other is the carbon and the zinc. All right, so that's basically how a battery works. So we're all on the same page in that. Now, one of the questions that comes up a lot is how does electricity flow in a wire? And the answer is that the electrons the answer is the electrons actually move through the wire. Let me pull this out a little bit so we can see. And so if this pipe represents our wire, and all this little paper tube I cut down, this ball represents the electron, the ball goes through the tube. Now I have to run it this way because I put a little crimp in there so the ball doesn't fall out on us so much. But if you think of the ball going through the tube and into my hand, I'm not sure if I can get this so you can see my hand. You see the ball comes through. It takes some time for that ball to go through. Okay? There's a little gap between the time I'm pushing it in. Okay? So if that were to take place when you turn the light switch, then it would take minutes, if not longer, depending on how long the wire is from the light switch to the light, for the lights to come on. And we know that we flip the light switch and the lights come on instantaneously. It's just bang. To our naked eye, it seems instantaneous. Well, what we're seeing here is what they call electron flow velocity. This is what we measure, is how long it takes an electron to get from one end of the wire to the other end of the wire. But that's not the phenomenon that turns our lights on. If we take and we fill this pipe with balls, now we got balls all the way to the end on both ends, okay? And we go to add another ball to it. You can see as this ball comes in, that ball comes out. And it's almost instantaneous. And if in a perfect environment, it would be instantaneous. You can't have two balls can't occupy the same spot at the same time. So if one moves, then the other ones have to move simultaneously. They have to move at the same instant. We know that that doesn't really happen. We can actually measure this difference, and that's because there's a little sponginess. These balls, as hard as they are still a little bit spongy, and so they move. Well, electrons going through a wire do the same thing. There's ether, and according to our theory, there's ether in the wire as well. And as these electrons are trying to bounce into each other, they hit the ether, and it's the ether actually that pushes from one to the other. So there's a little bit of sponginess in there. And that gives the time delay that we become used to. And the different wires will have different flows based on that, and also the ability to carry flow. So that is the concept of how electrons move through wires. Okay, so then this one comes out, and then another one's generated over here somewhere, and it pops in, and then another one's generated. And over time, eventually, as these go around, another one's generated, pops in, that pops up. And then finally, another one's generated, and out pops our ball that went in when we first started the experiment. So that's the difference. Now, one of the things I want to remind everybody is electricity has to flow through a conductor. Okay? Electromagnetic waves are not electricity. They're an effect of electricity, but they're not electricity itself. And that sometimes gets confusing. Sometimes we indiscriminately talk about electricity when we should be talking about an electromagnetic wave, and we sometimes treat electricity as if it was an electromagnetic wave. They're separate things. Think of ice floating in water as an analogy of how this works. Electromagnetic wave is the waves you would see if you push down on the ice cube in the water. They're the waves happening in the medium that we call ether, or energy in this theory. And the ice is the molecules of matter, or the particles of matter, the atoms, the electrons and protons, individually and collectively as bulk pieces of matter, like a piece of carbon or something like that. So, how do these electrons move through what appears to be a solid piece of matter, such as a piece of carbon, a piece of zinc, or a copper wire? And we're going to take a look at that right now. If we were to draw, let's start over on this side. We'll start with zinc. And we'll just draw a little piece of zinc here. And zinc is actually very porous at the atomic level. Okay? And so we're going to add all these little dots in here. And what these dots represent is a graphical representation of the density of zinc. You can see it, even with all of the with all these dots, zinc is still quite porous relative to these little tiny dots. I don't know if I can make them smaller, but little tiny dots of energy that permeate everything. Okay? Unfortunately, the scale here isn't working out for me like I wanted it to. But with all these dots of energy, you got that. So, what's interesting about this is how energy permeates. If you have a balloon and you can blow it up underwater, you would have to blow harder to blow that balloon up than you would in the air, because there's the pressure of the water in that vessel pushing against it. The deeper down you go, the more that pressure is. Well, the universe operates in the same way. It's filled with ether, and when you create matter, that matter expands outwards and it pushes the energy outward. It's what we call displacement. It's a displacement effect, just like a boat floating in water. Okay, so that was the eureka moment from many years ago when we were able to discover that if you put some water, if you take a ball of matter or something, a block of gold, and stick it in water, you're going to have, if you had a cup full of water and you stick it in here, you're going to have water flow over the side, and the amount of water that flows over the side is equal to the density, the amount of gold, if it's real gold. If it's not real gold, then you'll find that the amount of water will be less or more depending on what's in the gold. So That's a displacement factor there. When this starts displacing, there's a pressure gradient that develops around every piece of matter. Okay? And it would be like this. Now as you get further out from the matter, this pressure gradient, this pressure gradient varies off. So this pressure gradient decreases from the surface of the matter at a rate that is the inverse square of the distance. It's interesting. Thus, we have gravity. It's the same thing. Now, all this pressure is pushing in to the matter. So it's always trying to force energy particles into the porous matter. Okay, so now, this is if this is our zinc, right? Let me get back over here and write this. This is our zinc. Well, let's put some facts up about our zinc. Here. And first thing we want to know is that its atomic number is 30. Okay, so its number is 30. Okay, and its atomic mass is 65.39. Okay. Notice that the mass is a little bit more than double the atomic number. Thus, we have the concept of why we have to have neutrons to account for the extra mass of the protons. So the number of protons is what the atomic number is. Okay, and the density, I'm not sure if you folks can see this, but it's 7.139 grams per cubic centimeter. Okay, so for every cubic centimeter, we got 7.139 grams. Okay, so the next one we're going to draw here is let's draw copper. We usually use copper wire. Make this thinner so it's in the box. And then copper wire we're going to do copper wire about like that, and we want to have the same visual effect of energy inside there. But because there's more open spaces between the atoms, this copper is less dense, there's going to be more energy. That's what we're trying to show. Okay? But because this is more porous, the pressure gradients, the pressure on the outside is going to be a little different. So it's going to step off a little bit more you get the idea here. Okay, so we're still pressing in this way. Now remember, this is the weight or the force of the energy of the universe trying to refill that hole that created in it when matter appeared. Energy, when you think of energy or ether, what you're thinking of is the fluid form of matter. So energy and ether are the raw materials that become crystallized or solidified, okay, into matter. So matter consists of the same base substance, which is the energy in the ether. And ether is not a form of matter. That's why we don't see it or detect it. It's the other way around. Matter is a different form of ether or energy, just like ice is the solidified form of water. You won't find a million little ice particles, molecules making up water. You'll find millions of little water atom molecules making up particles of ice. Okay, so again we have that gradient, and if we look at the numbers here for carbon, a copper. So it's allowing you to confused. Copper is number 29, and its mass is 63.5, while its density is 8.96 grams per cubic centimeter. Okay, so you can see that it's more dense than zinc. Okay, and it's more conductive than zinc. I actually forgot what the conductivity of zinc was. I think it's somewhere around 70. But copper's conductivity is 100%, and zinc is somewhere around 76%, I believe it is, something like that. Apologize, I forgot what that is. Okay, so now let's go on to the next one. The next one we want to talk about is carbon. Okay, and carbon, again, is going to be less dense. I'm going to demonstrate that by putting fewer red dots in there. Okay, and we're still going to green. We're going to have lots of green in this one. There's lots of green. There, and then of course you do the pressure around the outside, and we demonstrate that by putting these pretty far apart like these there. Okay, so now if we look at the values for carbon, okay, here obviously it's 6, it's 12.01 for mass. And the density is 0.62 grams per cubic centimeter. Okay, and again, I forgot to I didn't write that down. I forgot the conductivity, but I believe it's slightly less than zinc. You might have these. But the conductivity is a little bit less than zinc. This might be in the 80s. Yeah, I apologize for not remembering that. I should take the numbers off on those. But we're not confusing ourselves. That's not that important at this point. Okay. And again, what we have is we have the pressure pushing force. So we have a force pushing inwards here. So if we wanted to discuss these in the context of, say, a comparison to something that we can touch, if we think of this here, which is our zinc, okay, as a submarine immersed in water, right? Right? The permeability of a submarine is virtually nothing. If water's getting in there, you got a problem. But there's some water that does get in. That's why they have pumps to pump it out. Okay, leaks around the seals or whatever, right? This, in comparison, would be a block of cement. So copper would have the permeability of a block of cement, all right? And this here, the carbon, would have the permeability of a sponge. So if you compare these three as a submarine, a block of cement, and a sponge, you can understand how water could get into those, and you see it's very difficult here, very easy here. The pressure on the outside of a submarine's hull is considerably higher than the pressure on the outside of a sponge, because the water is able to go into the sponge. So the difference between the internal pressure of the sponge and the external pressure is virtually nothing. It gets a little bit higher between these differences in a block of cement, and it's even less. There's even a greater difference. I should say there's a little bit more difference here, and there's even a greater difference here in the pressure differences between the internal pressures and the external pressures. This was a summary. So this is what we got going on in our materials that we're going to make our battery out of. So we always have these pressures pushing on that. And what we're going to see in a minute here when I draw this is why this is so important. We're going to see how it's basically gravity, the phenomenon we call gravity, which is a displacement force of energy ether by solid matter. And it's that force differentials that create the flow of ether, and along with ether moves the electrons. And it's just like watching water flow down a river or off, a fast moving water flow. The water flows, but inside that water is particles and electrons. So the bigger the flow is, in either volume or velocity, the larger the particles that can move with it. Now, all right, so we got this down. I wanted to demonstrate this fact to you. And we may look at that a little bit later in the video again. But, so we got that. All right. Now, do we have something that we can relate to that helps us understand this phenomenon that we're going to discuss a little bit better? And we do. We've all seen weather maps. And we see, the map of the U.S. and comes down here and goes up. All right? And that's a lousy U.S., but that's the one we get. Okay? And over here in California, they have a semblance of low. And you see a bunch of lines coming around there, and they go all out like this, all around the low. And then over here somewhere there'll be a high. And the same thing, you'll see the pressure lines. And they always aren't perfectly round, but they have different shapes. And so what these lines represent, they're called isobar lines. And what they do is they connect the dots of equal pressure densities. Okay? And what we find happening here is we have movement from this high pressure, this high density air to the low density or low pressure air. So we always have movement going this way. Right? You're never going to find airflow from a low density region into a high. That doesn't happen. You can't take water from the floor and connect a pipe to a tank up above it, and the water will flow up to the tank up above it. Okay, same thing happens here. We got high pressure to low pressure. That's exactly what's happening to create electricity. You're going to see that we have high pressure areas of energy or ether, high density areas of ether. They have a lot of force trying to push into that object. And then you have low pressure areas around objects who are more porous because the energy can just flow in. It doesn't build up that outside pressure, just like the difference between a submarine and a sponge. So there's our real world analogy to the problem. Now when you think about this, if you bring this high real close, if you have it over here, and you have the high pressure zone, right? And let's say you have a low pressure zone here, low pressure zone, right? But that low pressure zone, I'm going to move it here. Make this low pressure zone. Let's make this a big low pressure zone, right? Okay. And what I want to point out is if you're going from a small high pressure zone to a large low pressure zone, you're going to have the flow. When these come in contact, this flow is going to be very large. Okay? You're going to have a very high speed flow going in there. If this was a localized phenomena underneath a thunderstorm, what you're going to develop is a tornado. Because you're going to have the high pressure areas rapidly moving towards the low pressure area. And when that happens, then the tornado picks up matter in the form of, the cows in the fields, the trees, the rooftops, cars, rocks, stones, people, whatever, and it's going to move it with that flow. Okay, that's exactly what happens to create electron flow. Once we get the flow of the ether moving along from a high pressure area of ether to a low pressure area, it carries the loose electrons with it. If you created a vast enough difference in the pressures, you'd actually start moving whole atoms. But just like a tornado, a small tornado moves small objects, a very strong, powerful tornado moving a lot of air at one time would move large objects. So I wanted to demonstrate that. Now, if you have this the other way, okay, then let's just change it this way. Okay, if we would change this to the high pressure area here and the low pressure area here, what you have is less volume of flow. Okay, you have a less volume of flow. Let's put the lines. Let's see one line, but it'd be very fast. Very directed, because this is going to fill up so fast that it doesn't have time to get a large volume going. So you'd have a jettison like that of pressure. Okay, so let's get back to drawing our battery here, and we'll demonstrate what's happening on your battery. Okay. Now one more thing I want to draw and show you. Let's look at a copper wire for a second. If we look at a copper wire, and this is a wire. Inside this wire is a porous, and we're going to represent this porous, how porous this is to ether or energy by putting these dots in there. Okay, so all around this copper wire would be a field of energy or ether. And this isn't, there's no electricity flowing through this wire right now. Okay, we just have a length of copper wire. Okay. A simple length of copper wire, and we demonstrate that to ether, matter is very porous by putting these little dots in there. These just represent, as porous, and then you have around this whole wire, you have energy trying to get in. Now, obviously, the energy is coming in all directions, not just around here. So you also have, you could represent the energy coming across here, and you have energy coming across here the same way. So it would be a complete shell or sphere around the copper wire, including the two ends. So the energy pressure around this wire is the same all the way around. We're representing that by these lines, and of course, there is certain amounts of ether inside the wire. And we'll see how the presence of this ether is what creates electromagnetic fields around wire by it being pressed out. All right, so we wanted to show you that real quick. Now let's keep this in mind. Now let's draw our battery again. And this time what we want to do, we make the outside of the battery have some depth to it, thickness. So that we can demonstrate point. A little bit better. And we'll use the red blue. This is insulated cap. You know the cathode device, excuse me. Red is our cathode. And then inside here is our, I'm going to do a little wavy line. Inside here is our electrolyte. Okay, so around these surfaces, I don't have another color, so I'm going to use the blue up here for our insulated surface. This because I want to use the green to demonstrate our fields. So remember, this is a porous body. Demonstrate that with this. So around here, we have a field of pressure. We have a pressure zone. And that pressure zone is right inside. It doesn't matter about the electrolyte. It doesn't care about the electrolyte. You'll see in a second. And so we're going to demonstrate this. And of course, this radiates out as we get further away. It gets weaker and weaker and weaker. So we have a pressure differential from out here in the ambient, we call it the ambient density of ether in the universe. So right up close to this, we have a more dense, because again, just like the submarine, it has that hull. And the pressure against that hull, that water's going to be more dense because it's getting kicked back. You got a lot of weight pushing against that water. Creates more density. Okay, now inside here we have this, but also inside here we have a little bit of energy inside there where it's permeable. And we have the same thing happening around our cathode. Okay, I'm just going to draw one because it gets confusing. Now, inside of our electrolyte, if we were just to take a piece of electrolyte, you know our electrolyte is made up of kind of free molecules, just kind of loosely being held together in a fluid state. And here, our energy, or ether, actually surrounds each one of these kind of more like this. Each one of these is a separate unit. So we still have the same effect going on. It's just happening in a slightly different manner. What's important here is we're demonstrating that a single phenomenon, the displacement effect, when it's combined in its various ways that it happens, whether we have a very dense material, we have a less dense material, we have a pasty fluid-like material, it's the same effect happening at different scales. And it's these combinations of this happening that produce the many different effects that we see at our level of abstraction. At a very high level, we can't see all these little details happening, but we see the end results of them. It's just like a computer running. There's lots of little things happening. All you see is the picture on the screen or the words on the screen. You don't see all the little details that are happening down below inside the software and all the little switches, you know, that are activating inside and outside of all your chips to make things happen. Okay, so here's our battery when it's just sitting there. And it reaches a point where the energy pressures on here are balanced against the energy pressures inside here. All right, so there's no electron flow, even though our chemicals are in there, and this is conductive inside here, all right? Because the combination of one, this lesser energy density here, and this type of effect happening in here, balances out how much pressure is being pushed to keep these electrons in there. Now, an interesting thing that we hypothesize happens here is that if we were to look at a cross-section of this cathode, we actually get a line, right? That actually is made up of millions and millions of little molecules. Right? And in this case, we got carbon, so the atomic level, right? But and they're spaced somewhere, along the surface area or something like that. Well, our the electrolyte, you look at the density factors, you notice that there's that difference in the densities of the electrolyte. It's a little bit more dense than the carbon, right? What happens is this pressure front is pushing this way, and these little particles become bound to the carbon like this. So once you have this initial flow, okay, and if this is our carbon side, this is our carbon piece of that. If these up here, see, this is the wall of our carbon, right? You start to get what is like a check valve effect. Now there might actually be some that get inside here and actually start sealing up some of these other holes. So you have a little bit of penetration. For the most part, on the outside, you have a seal. That blocks electron flow going in there. If it was just the breakdown of the electrolyte chemically and creating electrons, the electrons would flow through the electrolyte, which is conductive, and would flow directly into the carbon, and it wouldn't come out through the wire ever. Because why would it go through a wire when it can go directly from at the surface of a contact surface? Okay. So now, let's see. So now we're going to connect our wire, and we put our copper wire up here. Okay, let's run just so you know it's a circuit for the resistor there, for references, right? So now, how does why does it flow down through here? Well, let's go back to this. If you look at this here, the lowest pressure of ether is going to be inside this copper wire. Once you connect this copper wire, and if you remember our wire, we had it like this, right? And we showed that the ether was all around it, right? The field it's not spherical, obviously, but it's like cylinder. It's all around it. The pressure is just like around a submarine. It's trying to get in from all angles. When you connect the wire electronically to this, right, you now break off this, and you connect the other end, and you break off that. So now what you end up with is a cylinder of energy that is surrounding this wire. And it goes up around the wire. So you're going to have a pressure density here of ether that forms around the wire. I'm just going to draw 2 lines. And remember, this breaks off. This reduces as you go outward at the same rate that gravity does. So it's a square of the distance. All right. Now, so this pressure gradient ends very soon in real life. around here you couldn't hardly measure the pressure gradients with the, there's no way you can measure it with a ruler. It's very, very close. But what's important is the internal part of this creates a hole. Now, because the density of our copper is, less than or equal to the zinc, right, we're going to have more electrons in here. There's higher pressure on here, so the energy coming in here is going to try to force these electrons around, and what's going to happen is they're going to pop down this little hole, because the density of electrons in here is going to be less. So they pop down the little hole. Let's draw this more like a pipe for a second. They pop down the hole and they get inside here. And now they're able to move through this less dense material. There's less atoms in there. There's less free electrons. Right? So what happens is we have a little bit of a chemical activity going on here. As the chemical activity happens, we get free electrons developing in here, right? And they block the entrance to here. They become one-way valves, so they can't flow directly into the carbon. The molecular matter here binds with the molecular matter here, so it creates these little check valves here. So we have increased pressure here. It's able to push these electrons, because what we have is energy trying to move down here, because it can flow into this. As it moves down into here, it's pushing along electrons. And this is why we have electron flow velocity, because it's actually moving the electrons down through the pipe a little bit of time, like I showed you. Now, what's interesting is there's also what they call a Fermi velocity. And the Fermi velocity is, that's Fermi velocity, E-E-R-M-I, okay? Now what that is how much an electron vibrates back and forth. Okay? Now what we find is that the higher the Fermi velocity is, the less conductive a material is. And why is that? Because if we have this circle and we have one electron, say we have two electrons floating around in there, right? And they're just barely moving, there's lots of space in here for other electrons to get by them. Okay? It's kind of like Indiana Jones thing where they got those arms swinging back and forth and he's trying to run in between them. And well, if you're running down that path and that arm hits you, you stop. Same thing's happening. If these things are moving back and forth and up and down, right, then there's less space in here. Even just by drawing arrows, you can see there's less space, right? And now it's more apt for a free electron to come in here to get bumped by one of these and stop. So now it gets stopped. The flow of ether is still moving through the hollowness of this solid copper wire, okay? And pretty soon it picks up the electron and starts moving in again. So what we find is as the Fermi velocity, right, is inversely proportional. The Fermi velocity, as it goes up, right, I want to say this in the simplest terms, the electron flow, this should be Fermi velocity, flow velocity goes down. So it's inversely proportional. That's what we call an inverse proportion. As one goes up, the other one goes down. Okay? We don't really have the convex of that is saying that as we push more electrons through, the Fermi velocity goes down. The Fermi velocity, the vibrational effect on these atoms or molecules is what drives how fast the electrons can move through. We can't get that through. Now, Fermi velocity is directly proportional to temperature. So the higher the temperature goes, the more the Fermi velocity goes. The lower the temperature goes, the lower the Fermi velocity goes. So that's why we have superconductors at very cold temperatures, because when the molecules are sitting still, it's easier for the electrons to pass through. Now, in our DC current, we're going to get a flow through here, and what we're going to do is initially, these electrons are going to be very dense along this line. So we get a lot of electrons moving along here, okay, and they start coming. And we're trying, what's constantly trying to happen here is everything's trying to normalize. It's trying to equalize pressures. As this pressure becomes equalized and it gets all the ways around, right, then pretty soon we have an electron pop out here. This initial flow of electrons is what creates our electromagnetic field around a DC circuit. So when we first turn a DC circuit on, okay, we create this. Now, why does that happen? What happens is, as a new electron comes in here, it displaces some particles of ether. Now those particles get bounced outside of the wire back out into the field. And if you think of this happening billions of times every second, all right, to us it becomes a solid field. So what it does is it actually starts increasing the density of this field. Okay? Now, in a DC current, these electrons flow through there one time, and they get deposited. I got my black right here. They get deposited inside here. So it's just like our little tube we showed you. You push one in this way, one has to pop out this way. Now, because this is not completely back-to-back electrons like our tube has balls, there's some elasticity in there, and that's what gives you the delay time. That's why it's not a complete instantaneous, when you flip the switch, instantly the lights are on. There is a slight delay, but it's a very small delay. However, how long it takes this particular particle to move to this point, to move to this point, to move to this point, to this point, and then finally into here, okay, that time is going to be considerably longer. These particles don't move very fast at all. I got a little clip here I'm going to show you right now, and it shows a particle of, somebody put this together, and I thought it was really good, so I didn't do this, but it shows a comparison of a snail moving around a circuit to how long it takes an electron. So why don't we watch that for a second, and then we'll come back and finish explaining this.
How fast does an electron move down a wire? Which would win in a race, an electron or snail? Let's answer the second question first. You may be surprised to learn that the snail would win, easily. Let's use this electrical circuit as our racetrack. It has an on-off switch, a battery, and a light. The distance around our racetrack is 22 inches. According to the 1999 World Almanac and Book of Facts, a garden snail can move at a whopping 0.03 miles per hour. That's 0.528 inches per second. We'll call her Joan. The 1998 Guinness Book of World Records says that a garden snail named Archie went a whopping 13 inches in 2 minutes. That's 0.108 inches per second. This is Archie. And here's our electron. We'll talk about how fast it moves later. And they're off. Archie and Joan roar ahead with the electron. Well, it's moving, but doesn't look like it yet. Joan's in the lead, and Joan zooms ahead with Archie behind, and then the electron... Well, this will take all day, so let's fast forward it. And the winner is Joan, with Archie well behind, but our electron has moved a mere 1/10 of an inch. But doesn't electricity move at the speed of light? The speed of light is around 300,000 kilometers per second, or 186,000 miles per second. Actually, in an unshielded copper wire like this one, electricity moves at around 96% the speed of light, so 178,560 miles per second. At that speed, ignoring other losses, electricity could circle the globe over 7 times in just 1 second. So electricity moves at close to the speed of light, but the electrons don't, as we saw with our little racetrack. One way to visualize what's going on is to use this row of marbles. When we push on one marble, the effect of that push is passed on from marble to marble, and the result is felt by the wooden tile almost immediately. The individual marbles represent individual electrons. They don't move very far along the way. Electricity is represented by the effect on the wooden tile. That effect is passed on almost immediately. And to answer our other question, how fast are the electrons moving? The electrons move at a velocity called the drift velocity. Here's one easy formula we can use to find out. Calculating it out, we get 0.0007 meters per second, or 0.0028 inches per second. Remember, our slowest snail, Archie, goes 0.108 inches per second, 38 times as fast as the electron. For the electron to go around our 22-inch long track, it would take 7,857 seconds, or around 131 minutes, ignoring the time spent in the battery, switch, and light.
Okay, so you saw that little clip, and it's kind of cute, but it really brings the point home. The electrons themselves move very slowly through the wire, but the effect of the electrons being pushed into the wire at one end, because an electron is such a small diameter that each one pushed in only moves just an infinitesimally small amount, but it pops one out at the other end every time. All right, so this is really busy. I appreciate that, but that's really what's going on around the circuit. Now, why a DC circuit doesn't have the same type of field around it like an AC field, and like you put DC through a transformer, it doesn't do anything, is because once this density of electrons normalizes, right, it's going to stop pushing pieces out. In other words, when one comes in, one goes out, the volume available inside this porous copper for the ether remains the same. So you don't have ether going in. Now, if you pulse this, in other words, if you put a switch in here and turn it on and off, turn it on and off, you're going to create a pulsing pattern around here. And that's exactly what we see when we step up a level in our level of abstractions. We see fields creating and being completing around a wire, a pulsating circuit. And the same thing happens if we were to use AC. In an AC world, we're pulsing these electrons back and forth, so we're taking them out, putting them in, taking them out. And in doing so, we're collapsing these little particles of ether able to move in and out of the porous wires, and that's what gives us our continuous fields around AC current. That's another story, but okay. So now what happens is, eventually, you start to get a buildup of electrons inside here. Okay? And now the pressure on these electrons starts to increase. The copper becomes a little bit more dense as it gets more electrons. Well, as that starts to happen, I'm going to represent the electrons coming in with this black in here. We start to get pressure inside here, okay? And as we get enough electrons, we have to force energy or ether back out. We open these little one-way valves. So now our electrons can flow out this way into our electrolyte. And this will continue to happen. Now, as the electrons flow back into the electrolyte, it stops the chemical reaction. As each one of these little bodies stops producing a push, as it recaptures the energy and holds the energy. We talked in our video on gravity on how on the atomic level we hold energy within the shell, we hold ether within the shell. It recaptures that energy and it stops putting so much force on here. So what will eventually happen here is these movement of electrons will flow in here, and we come to an equilibrium point, and that's when our battery dies. And when there's not enough push on here to force any more electrons through this tube, because they can't come out the other end, so the pressures on this side of the tube of the wire equal the same pressures on the outside of the wire, that's when the electricity stops flowing. So that's a very simplified version of how do we get electricity to flow through a wire. Um, there's a little bit more detail, and it will take quite a bit of time to discuss how all of the specific interactions between the electrolyte and the carbon, the zinc, would happen. But I wanted to give a higher level overview, a simple overview of how this is happening. What we're proposing here is something that the other theories can't explain. There's nothing in quantum mechanics that explains why this electron flow should happen. Why doesn't the charges go directly into the carbon? If they're being produced in the electrolyte, then it's closer for them to go directly from the electrolyte into the carbon. They go into the carbon because they go down the wire and come into the carbon. We know that. So why isn't it not? Well, this is an explanation, and the point here is to get people thinking about this. Experimentation or whatever may someday prove us wrong, but right now the observable phenomena and the analysis supports this theory, and it keeps the concept of the ocean universe, a gravity-based universe that creates other phenomena, going along a single explanation. What our goal is to be able to use the most fundamental basics of as we get a particle of matter and it forms anywhere in the universe, that immediately it displaces the energy that existed there. So all these little tiny dots, if this is an electron, these little tiny dots are probably even still too big for the particles of energy, but you create this displacement field around every single particle of matter. And using this one basic concept, we were able to explain how a battery works and why it works the way it does. And that's what we're trying to go here. Where we're going with our theory is to use this simple phenomena to explain all of the things that we see in the universe. Now, one interesting aspect of this, and I think we need to remember, is this. Things like electricity happen because of this, but this really isn't electricity. Electricity ends up being an effect of gravity. And so while electrical effects that we can see on Earth and in space are real, the underlying cause of what gets the electricity to move, what creates the electromagnetic waves, is all based on this simple displacement factor. And that's really a powerful understanding. And by combining different types of displacements, we can develop all of the effects we see in the physical world. So that was our session for today. Hope you enjoyed it, and we look forward to seeing you on future sessions of the Ocean Universe. Thank you very much.